As part of the FUI PILAS project, in collaboration with IDEMIA, STMicroelectronics, SERMA and Alphanov, the Hubert Curien Laboratory has experimented the possibility of making fault with a 4-spot laser bench developed by Alphanov, and this is the only 4-spot prototype developed in France. Here is the Alphanov laser bench. It allows to attack the flash memory of a 32-bit microcontroller, which will be the target of the attack. The technology of this memory allows to realize bit sets. That means to set bit to 1. These bit sets will be realized by the 4th spot in the flash memory. Having a multi-spot laser bench prevents us from the spatial and temporal constraints we have with a single-spot laser bench. Indeed, a laser can make either one bit set or 2 consecutive bit sets. In addition, a single-spot laser bench is limited as it can only strike one place at a time. The following experiments shows faults realized on a move instruction, which allows to put a value in a register. In this experiment, a register is set to 0 to better see the laser sets. We follow this instruction with 1, 2, 3, and then 4 lasers. The first experiment consists in faulting a byte of a register with a laser. This laser succinctly attacks all the bits of the bytes, starting with the most significant one. For the experiment with 2 lasers, the first laser is fixed on the most significant bit, while the second goes through the 4th least significant bits. When all the least significant bits are seen by the laser, the first laser moves on to the second most significant bit. Then the second laser goes through the same 4 least significant bits again, and so on until the first laser strikes all the most significant bits. For the third experiment, 2 lasers are fixed on non-consecutive most significant bits, and the third laser goes through the least significant bits of the byte. Finally, for the last experiment, the lasers are arranged so that they are all separated by 1 bit, and then they move 1 bit to the right. Thanks to the bit sets that we can perform, we can change the operation code of the instructions. The graph here shows all the operation changes we can make from an AND operation. Its operation code is the weakest, 0000. So it's the operation where we can make the most changes. For example, if we want to switch from an AND operation to an OR operation, we must perform a bit set on the last bit of the opcode. Thanks to these experiments, we notice that with 4 lasers, the limit of a single laser are removed. Indeed, we can realize very precisely several non-consecutive sets of bits, which give us more possibilities, especially in the change of operations. Moreover, time constraints are less important because instead of using one laser that will move around, we can use several lasers at different locations.